Okay, this is just going to be a quick video where I just show how to edit packages efficiently, just how to do this in a very interactive way. So right here I have simple diffeq set up in my Juno. And so what I'm doing right here is I'm going to add an Euler Maruyama method. Let me make sure I spelled that right. So Euler Maruyama. Yeah, that's why I don't like the... Okay. So I'm going to then add a Euler Maruyama.jl. So what simple diffeq.jl is it's a library of just simple differential equation solvers. The reason why I'm building this is so that way contributors will have well, three reasons is so that way we have something to benchmark against, so that way we have very simple versions that we can cross-compile to GPUs, and so that way, and also so that way I can have a nice style guide for how some things should look inside a diffeq. So simple repo, you can see that there's a very simple function map. It has an integrator with stepping, and it also has just a solve that just does a loop. So no callbacks or anything like that are supported. It's just, this is what simple diffeq code looks like, and what I want to do is I want to make the Euler Maruyama version of that. So if you look it up, the Euler Maruyama method is just, you take a stochastic differential equation, you update it by multiplying by dt and multiplying by a random number. So what I already have in the top level here, diffeq base. And so now that I already have diffeq base in here, what I want to do is I want to create an algorithm and overload solve. So here what I'm going to use is simple EM, so simple Euler Maruyama. And what I want to do is I want to override the function diffeq base.solve for an SDE problem when someone calls it with the simple EM algorithm. And the only option I'm going to support here is the GT option. Right, so just so that way everyone's on understanding what's going on here, differential equations. If I go over to the documentation, the only options which we have inside of this part right here for solve are the ones listed as the common solver options. Anything else would go into the algorithm. There's tiny exceptions for the different problems. So for let's say, for example, the SDE solvers, you can have special keyword arguments. So you can also have save noise and delta. I'm not going to support that in the simple version. So yeah, so those are like all the args. I'm just going to support a few of them. In the future, what I might want to do is add warnings for the ones that I don't support. So I mean, if you probably have noticed that in diffeq, that if you call an algorithm with options that aren't implemented for it, it warns you and tells you that it's ignoring it. So here, I'm actually going to make it error because I don't know how to make it work without a DT. So DT required for simple EM. And so now I'm just going to implement the Euler Maruyama method. So in the Euler, or in this, what I'm going to do is I'm going to create a test. So simple EM test.jl. And inside of here, I'm going to create a stochastic differential equation. So I'm just going to write what a user code would look like. So using simple diffeq, and simple diffeq, this re-exports diffeq base. Let me do this in a fresh session. So I just did Control J, Control K to quit Julia. Control J, Control C will then clear the console. That gives me something brand new. I click over to the REPL, I hit enter, and now I am in a brand new REPL, right? And you can see that this is grayed out. That tells me that it's new. And so let me recompile everything. Hopefully that doesn't fail. This is... Ugh. Okay, did I misspell something? Maruyama. Mary. Yeah, there we go. Okay. So when I do control, there's a few commands I'm going to be using here to do the interactive side on the left. Shift enter. So if I shift enter, it goes down to the new line. If I control enter, it evaluates on the same line. Right. And okay. What I'm going to do here is I'm going to create a stochastic differential equation. So if I do something like f of upt is 2u and g of upt equals 1, then this is the stochastic differential equation. Dx of t equals 2u dt plus dw sub t. And I want to give a initial condition and a time span. And then this makes an SDE problem. And there's no parameters. All right, so that's my SDE problem that I want to do. So this setup is called test-driven development. What I'm doing is I'm writing the test before I even write the code. So that way I know what I want it to do. So here, what I want to do here is I just want to solve this problem with simple EM. So now it's saying that there's no method solve for this because I haven't really written anything. So now I'm going to actually save that file. If I run this code, so what I did here is I clicked over to the package code and I just evaluated some functions. When I evaluate that function in the package code, it'll actually update the code in the package. So when I jump back over to my test script, now this is the new code. So if I do something like dt gets 0.5, it's now doing nothing. So let me jump in here then and go, okay, let's, so the first thing that we want to do, let's just unpack a few variables. Prob.f, g gets prob.g, u0, and let's see, tspan gets prob.tspan, right? And now what I want to do is, let's see, so n, the number of steps, is going to be prob.tspan of 2 minus, or I can just do this as tspan of 2 minus tspan of 1 divided by dt. Right. And I'm going to just enforce that this is going to be an integer, so this will be enforcing that the result has to actually be an integer or it will error. So I'm just, for now, just not going to support handling the extra on the end. And so what I want to do then is I want my solution array to be created from my initial values for u in 1 through n. So let me make sure that that's good right now. In value, oh, I didn't give it a, so here I evaluated the function in place. Now what you see is this actually does something different. So Julia by default will return the last thing that happened. So it's returning what this u is. So I did dt equals 0.5 and it's returning an array u of the initial condition 2 times. Let's make sure that this is good. That looks good, right? T should then be t equals I times dt for this t-span of 1 plus I times dt for I in 1 through n, right? And this is good. That's almost good, right? But we are missing our initial condition. So we're actually, what this is actually showing me is that I need to have one more. So that way I have, what did that look like? Oh, okay. This needs to be like that. So it wasn't off by one error. Yay. Let me just close that because it's tripping me up. I name test files test.jl all the time. So actually what I want is that, and so I'll just match it here. Okay, so now actually it's probably better to just make that +1. So okay, so now let's do the Euler-Maruyama method. This is just going to be for I in 2 through n. And so what I'm going to do in this loop is I'm going to say that u at the next value equals f of, so u prev equals u of I minus 1, and t prev is t of I minus 1. And so the algorithm is, let me grab the parameters here too. So p equals prob.p, add a space for good measure. Then this is going to be u prev p t prev times dt plus g of u prev p t prev times square root of dt. Let me voice this out of the loop. I'm pretty sure Julia would actually handle this, but this is just to be safe. So square root of dt times a rand of, now let me just play with this over here. So rand n is like that. I also want this to support static arrays. So if I do rand n of, so if I make a static, or at s vector 2, 3, 4, rand n of a, what does that do? That's not good. Let's see. So then what do I want here? I want, this might be something I should just handle later. Because I want to get a random number for each of the values that, and right now it'll only support scalars. So I'm just going to throw open the static arrays.jl, and oh yeah, so I want to do this by size. So I'm just going here and going, okay. So if I do size of A, and that's good. And if I do size of 1.0, that is not what I want. So then let me just do handling here. So if I then add using static arrays, I evaluate that, that's now in scope in the package. So if, let's see, so if uprev is a stat s array, then r gets rand n of size of uprev, else r gets rand n, And from there, what we do is that. I think that's right. So TU, let's just output those two things for now. And let's check how our function's doing. So type error. So when I click here, I click on the stack trace, it brings me right to where the error is. The error is that this is supposed to be a type, not the actual value. I evaluate that in place, and now you see that I get times, and I get the values. So yeah, and then right here, what I do is then I do things like add test sol.t. Well, sol.t should be equal to 0 by 2.25 to 1.0, right? Let me add base.test in here. Oops, I just evaluated everything. So, okay, why is that not the same? Can anyone guess why this is not the same? Oh. So let me collect this so that way I get an array here. And you see, boom. See, what this printed out is that this value is an array, this value is not. So equals equals just didn't handle that. Anyways, so let's make sure that the length of u is 5. Here, what is u? U is, oh, that's an equals. And there we go. Now we have some tests. Now, if I want to check that the type of u is a DE solution, right now this fails. So I can add at test broken, and that tells me that this test is broken for now. Now what I'm going to do is add simple em tests. So simple em test.jl. I'm just going to make sure really quickly that it runs. You see that there's a pass, a broken, and a total is 3. So why broken is nice is because A, it will throw you an error if it ever gets fixed. So, I mean, that's a quick way to be able to tell you, hey, you accidentally fixed something. But also, what's really nice is that it tells you it's broken. You can track it that it's broken, and you can just make sure it's broken. The other way to do this is to comment out tests. And once you get any significant amount of code, your tests which are commented out will get lost, right? You'll just forget that they exist. So by doing this, this way you have a nice tracker for all your broken tests. So then to run our tests, you do pkg.test, simple diffeq. And then this will run this test suite, which will do the discrete test for that function map, and simple em, which will test our Euler-Maruyama method. So while that's running, I'm just going to grab some code over from this function map, which is just how the heck do you create a DE solution? Simple em was not defined. Oh, because it did not export it. Okay. So now let me bring this in place here to make sure this works well. So okay, so by adding the export, this actually works now. So the issue that I had was that when I did this include, it actually included some stuff into my global scope, but fixed. And now what I just did here is I made it so that way it returns a proper diffeq solution. So this will probably do something weird now. Instead, it should be a solution object. and now I should say sol.t and sol.u, and this will actually pass now. And so this got an unexpected pass, so I should change it to @test. And there you go. Now this test file should be good. If I do simple diffeq, then what this will do is this will run my package tests and make sure everything works. In the meantime, because I know this is probably going to pass, let me open up simple diffeq.jl. You see that these are my commits. I'm going to review my commits, make sure that they all look okay. And what's this? U not defined. Oh. Sol.u. So what's going on here? I can pull this down and nope, I want to do sol. There you go. So yeah, I hope that this video just shows off a nice interactive workflow where you're basically just going between your test function and your package code very quickly. I actually like to do this for my research codes as well, because then you have, @test, making sure that your research code always works, and you have your longer functions then as your package for your research. Actually, I do this and then I release the research as a package. And that's how diffeq came about. So hopefully this gives a nice way to show you how to use Juno to do package development really quickly. As a last step here, just reviewing the PR, everything looks nice. If I needed to pull something out, like if I had an extra test in here, let me see if it, yeah, so if I had like a extra blob in here that was bad, you can just go to discard hunk and you can get rid of parts of it. Let me just show you one last thing. One easy way to see what's going on is if you just @show inside here. So if you @show, evaluate, and then you'll see that it tells you, so @show is nice because it prints out the name and then equals. So yeah, that's some nice stuff for just working in Juno. Hopefully that helps you out. Cool. Let's do this and push. So add out of place simple em. So both of these are actually pointing to the same thing right now. That's silly. And then if I check online, nope. Simple diffeq.jl, you see that out of place simple em is there. So I can push the master because it's my repo and I have all the power in the world. If it's not your repo, then what you need to do is you need to go fork it. When you fork it, you add a remote to your fork, so you can see that George has his own fork actually on this repo. And then what you can do there is you can set upstream to your branch, and then you'll see it over here. What this will do is it'll make it push to your fork, and then you just drag and drop, and that'll open up a pull request. So in that setup, you can use your own fork just like it's your own repo. It is your own repo. But whenever you want it to update the code in the actual package, you need to do a pull request, and they need to accept your code changes. Other than that, that's pretty much how you do test-driven package development in Julia.